I'm Jennifer Niemann, and I'm going to be talking about my research project, Statistical Modeling of Environmental Data with Non-Detects. So the motivation behind this project is that in the environmental sciences, it is very common to have observations that are not able to be detected by the measuring device, and so they are only reported as non-detects. So for example, if you have concentrations of arsenic in soil samples collected after pollution, and let's say the detection limit is 5 milligrams per kilograms. So anything underneath this value is not going to be detected. So the question is, how do we analyze this non-detectable data? We know it exists, but we don't know anything except that is underneath a certain value. So in statistics, this type of data is known as left-censored data. There is currently no singular preferred method for working with such data. So this research analyzed several different statistical techniques that can be used when dealing with left-censored data. So I used three main methods in this research, including substitution, maximum likelihood estimation, and the Kaplan-Meier method. The substitution methods were used simply by replacing the non-detect observations with 6 different values of substitution. That included 0, the detection limit divided by 2, detection limit divided by square root of 2, evenly spaced values between 0 and the detection limit, and random values between 0 and the detection limit. So just to illustrate quickly, let's say you have a sample of size 10, and since this is a simulated sample, we do know that the mean is 4.3. But let's say that there is a detection limit of 3. So then everything underneath the value of 3 becomes censored, and then we have a censored sample. And then using our substitution method, we simply substitute in each specified value in for all of the censored values, and then once you have that new sample, you can find your estimated means, and you can compare those to the actual mean. Since in this case it was simulated, we do know the real mean was 4.3. So moving on to maximum likelihood estimation. This method assigns an assumed distribution to the data, both the detected values and the proportion of censored observations. So using the assumed distribution, which in this case I use the log normal distribution because it has a positive support, and this aligns very well with environmental data because all the measurements will be positive, for example, that contaminant in soil. So then we can use the likelihood function, which is known to be the product of all of the probability density functions, but that is used when all observations are detected. However, in our case, we need to account for detected and non-detected observations. So we can bring in the cumulative distribution function because the definition of that is just the probability that y is below some value, which is exactly what our censored observations are. So going back to our example, we had the 4 censored values, and those can just be plugged into the CDF, and then the observed values can be plugged into the PDF, and we can find our estimated log normal mean of 4.54, and then remember that the known mean was 4.3, so you can compare those values. The next method I used was the Kaplan-Meier method, which is a non-parametric method, and it is very widely used in survival or lifetime data analysis to estimate the survival function, and then it is used to estimate different summary statistics. So the Kaplan-Meier estimator of the survival function is given as follows, and then you can use this formula to find the estimated mean with the following integral, and then it can be estimated with the following sum. However, the Kaplan-Meier does require right-censored data, so our left-censored data must be transformed into right-censored data, and that can easily be done. I'll show you with our example. It can be done by subtracting all the values from a fixed value that is greater than the maximum value in the sample. So if we subtract everything from 9, which is greater than our maximum value, we can end up with a right-censored sample, and then using those to find all of the values needed for the survival function, we can find our estimated mean for our right-censored data, and then we can also find the estimated mean for our original left-censored data, which is 5.02. And you can again remember that the real mean was 4.3. So after defining all of these methods, used different criteria for assessing the effectiveness of each method, and that included bias, mean squared error, confidence intervals of the mean, and upper tolerance limits. So bias is a measure of how far off the estimated parameter is from the true parameter. So you can see with this equation here, it is the expected value of the estimator minus the parameter. And statistical bias of an estimator is just the expected amount of over or underestimation done by the estimator while estimating the parameter. And the estimator is said to be unbiased if the bias is equal to 0, so that the expected value of the estimator is equal to the parameter. So the mean squared error of an estimator is the mean of the squared error. So in other words, the mean squared error is a measurement of the amount of squared deviation or squared error that the estimator displays on average. You can see it has a direct relation to bias. The MSE is the variance of the estimator plus the bias of the estimator squared. So if bias is 0, then the MSE is just going to be equal to the variance. And for this research, we were wanting bias and MSE to both be at a minimum, indicating biasness, unbiasedness, and small deviation. And as I said, they are directly related, so if an estimator is unbiased, its MSE will be at the minimum value. Confidence intervals, you can see it is a standard confidence interval formula, but in this case it was exponentiated for the log normal mean. It is the estimator plus some t-value plus the standard error of the estimator. And in this case, I did use alpha is equal to 0.05. So in repeated sampling, it is expected that 95% of the random samples will produce confidence intervals enclosing the desired parameter. And for this research, the most effective method will produce confidence intervals with actual coverage very close to that pre-specified 95% confidence level. So the upper tolerance limits do provide more information about a population than the confidence intervals do. The confidence intervals were just telling a range of where the population parameter could be, but upper tolerance limits actually tell you basically the percentile of a population, and in this case I used P, the content, is 0.9, and alpha was again 0.05, so the coverage was 95%. So our upper tolerance limits were indicating that 90% of a log normal population lies at or below the upper tolerance limit with confidence level 95%. And the most effective method will produce upper tolerance limits with actual coverage very close to that pre-specified level of 95%. So in order to test all of this, I created simulations in R with the NATA package, and I created 1,000 samples of size 50 from the log normal distribution, and then I simulated censoring and then performed the various methods. I also did perform all of these methods on 2 detection limit scenarios, so I do have results for that as well. So this is for the single detection limit scenario, the bias and the MSE. So just looking at this graph, the best methods will produce bias as close to this 0 line as possible. So that was substituting with the detection limit over 2, and also substituting with evenly spaced values and random values between 0 and the detection limit. The MSE values, you can see that all of the methods, except for the maximum likelihood estimation, produced MSE values that were very, very small with the 1 detection limit scenario. Then with the confidence intervals and upper tolerance limits, we were wanting to find methods that were close to this line right here that is 95%. In looking at both of these, it looks like substituting with the detection limit over 2 provide good results up until about 30% of censored observations. Anything that is much higher than that 95% line is much too conservative for any actual useful analysis. So moving on to the 2 detection limit scenario, in this case I used 4 different detection limit for the first detection limit, and then the second detection limit was varied from that first detection limit up to 60%. So this is bias, and looking at all of the different levels of the detection limit, it looks like the substitution of the detection limits divided by square root of 2 is the best substitution method. And then looking at the MSE, again, they're all quite small values of MSE, but overall, moving on to the highest level of the censoring, it looks like, again, substituting with the detection limit over square root of 2 is actually the best. And then looking at the confidence intervals with 2 detection limits, actually all of these confidence intervals are much too conservative for any practical analysis. So moving on to the upper tolerance limits, it does depend on the censoring value in this case, because it looks like when the first detection limit is set at 20%, the substituting with the detection limit looks very good. And then at 30%, it looks like substituting with the detection limit over square root of 2 is very good. And then moving on to the detection limit at 50%, the detection limit over 2 is the best method. So based on these 4 criterion for selecting the most effective method, I do recommend using the substitution methods of detection limit over 2 and detection limit over square root of 2 in both single and 2 detection limit scenarios. And this is actually quite consistent with what is actually used in environmental sciences and the industry, because they do produce fairly good results, as we have seen, also without having to specify a certain distribution for the sample. Using the parametric methods such as the maximum likelihood estimation depends on having a sample that is a good fit for that specified distribution, and this is very difficult to do in practice. So just very quickly, real-life example. This is from the very first example I mentioned, the arsenic concentrations in soil, and the detection limit was 5. So there are quite a few censored observations indicated by the less than 5. First, I fit the data to the log normal distribution with a QQ plot, and you can see it is a very good fit for that distribution. And then I ran all of the methods with that data. But just looking at one of the methods that I recommended, the substitution with detection limit over square root of 2, the estimated mean would be 5.584 kilograms per kilograms of arsenic in that soil. And then looking at the upper tolerance limit, that tells us with 95% confidence that 90% of the arsenic concentrations are at or below 8.8184 milligrams per kilograms. So that tells us a lot about the data. So thank you for listening, and if there's any questions, I believe there's time for that.
Hi, Jennifer. So the question is, as your project was quite exploratory, what were your expectations going into the project, and how were they met or surpassed?
Well, actually, since I did simulate my censoring with log normal distribution, I really expected the maximum likelihood estimation to be the best method, since it is based on the distribution. However, it was definitely not the best method, and me and my advisor were actually trying to brainstorm why that happened, and it's still quite unknown, but it's a mystery, but they do actually use the substitution methods in the industry, so it was puzzling.
And another question is, how did you originally get involved with this research project?
At Marshall University, all statistics majors are required to do a capstone project, and I was just very fortunate that my research advisor, he was able to work with me and he helped me come up with this project, and he guided me on the project, but I was just very fortunate at Marshall University. They do encourage all their undergraduate students to get involved with research.